Okay, yeah, good. It's recording. Okay, so yeah, we have to see a bit more about things. So we are doing this Dirichlet series, general properties, and so here is a proposition with P. Let F n, they said for us, it's always one to set of natural numbers to see the a multiplicative sequence. Say, and so how to formulate it then? Yeah, sigma n. Yes, from one unbounded by then we say this is equal to, so there is a kind of weak form of Euler product formula for this. It's not as nice as Euler product, Euler factors. Each term has infinite number of terms, but still there is that's here. So that's phi. And then there we get 1 plus e minus s plus f of 2 minus 2s plus f of 3, so on. So this is over all primes, and this is true for real part of s. So this is in the spirit of Euler product formula, but as I said, it's not quite like that because this is still kind of infinite sum inside each factor. So, but this is the beginning of. So where we are going to use, you think that f is bounded? How we use this boundedness of f? Yeah. Brings in any result you might think would be relevant for this. That's right. It's used for convergence of this by results that we proved. Already forgot. It guarantees that the series on the left-hand side is actually convergent for real part of s bigger than 1. That's now I think I know. Okay, so now I know what it is. I mean, just you can bound it, take absolute value, bound it, and then this is like bounded by some like zeta series, which we know is convergent for real part of s bigger than 1. So that's so by the first result about the Dirichlet series domain of convergence that we proved, follows that this is the left-hand side holomorphic function for real part of s bigger than 1. That's so this is what boundedness gives us. Actually, we have a domain of convergence for the function. But the thing is, the right-hand side is also defined, and the two sides are equal for real part of s. Good. So how does it go? So let E be the set of first n primes. First n primes. And let n of E be set of all integers that you can construct using only this prime. So the set of all integers that this prime only appear in their prime decomposition. Set of so all integers of the form. So these integers are of the form, say, a equal to p1, n1, p2. So that's 1. And pn, kn, well, ki of pn. So all integers in whose decomposition only these first n primes are used. This is that's true. And I'm going to let n go to infinity. Okay, so now then just write this thing. So then, so imagine you have a number which is of this form. So f of k over k to the s. So we can write it as 1, 1, 2. And so, I mean, f of this divided by 1, 1, 2, 2, and of course, I should not forget s here. But because f is multiplicative, and multiplicative means that anytime you have two things relatively prime to each other, you can decompose the values of them, right? Only in that case. So these guys are distinct prime, so they are relatively prime. That's what right? I think that's what we want. A1, 2, 2, and divided by 1, A1. So sorry, SK2. Then I can use, so now I just choose some part of the left-hand side, which is only I use those ends which appear in this set N of S. So then left-hand side, not left-hand side, but partially left-hand side. So I get something like sum f of n over n to the s and n belonging to this set n of p. And this p is, this is about, is the set of primes. So, okay, n belonging to n of p. Of course, by this, we can just write it as sums of distance f of p1, k1, f of p2, k2, and then f of pn over 1 e sk1 e2 sk2 and en. Okay, so this is now the sum is over all k1, k2, kn bigger than equal to 0, right? Over k1, k2, kn bigger than equal to 0. Then we can use a very simple identity from algebra, which is something like this. I can just say sum, for example, for 3 terms. Imagine I've got n terms here, but imagine you have some 3 terms, ai, j, k, I, j, k, all of I, j, k from 1. Imagine this are conversion, but in this case, you just write it as sum of ai times sum of, this is bad, sorry. E, j, c, k, sorry. Sum of ai, sum of bj times sum of you can switch the like sums of products become products of sums by distributing this. Okay, so we can, yes, sorry. Some P is this set only. Okay. And N of P, capital N of P, is the set of all integers of the form. So all integers in the prime decomposition, only 1, P, 2, P, N are used. The first N primes are used. But they are infinite, right? Because you can just raise these powers higher and higher powers. There are still infinitely many integers that belong to this set. Not all, but infinite. So we are rewriting this as infinite sums of infinite things. But just the first part is just the first n primes are used. Right? Is that clear? Any other questions? All right. So using this, then I can decompose the right-hand side as products of the things. So this means that right-hand side of star is equal to, well, then you just write it. Okay, so you just get 1 plus, I mean, oh, I made a mistake somewhere. Oh, no, that's okay. This is good, plus f of p1, p1 to the minus s, plus f of p1 squared, 1 power minus 2s, so on, times 1 plus 2 to the minus s, plus f p squared p to the power minus 2s. So then 1 plus f of en minus s plus f of p squared. Oh, sorry, n squared power 2s. So this sum, which is an infinite sum, is equal to products of these terms. Each of them are infinite sum. Sorry. Okay. Then what we do? Let n go to infinity. And let n go to infinity. And you're done. Because if n goes to infinity, on the left-hand side, you are producing all integers. And on the right-hand side, you're getting all the primes. And that's so this is also a proof of Euler product formula for a special function. If f is identical equal to 1, this gives us a proof of Euler product. But I mean, it doesn't quite give us that because there is a geometric series argument that I will provide right now, but this is the same. But this is kind of useful on its own, this sort of weak form of Euler product formula, as I say, the weaker form of Euler. Okay. Question? Comment? No? Okay. If there are no questions, then I can now look at a special case where f is actually strictly or fully multiplicative. That happens. Let's see what happens. So corollary of this result is that so corollary will be like this. If f, I call it fully multiplicative, right? I believe Searle calls it strictly multiplicative, something like that, but they have different names, but that's okay. F is fully multiplicative. So this means You remember what was fully multiplicative? It means just f of mn is equal to f of m, f of n for all m and n, without any restrictions on m and n, i.e. f of n, f of n for all m and n, we can make 1, then we get sum f of n over n to the s, and from 1 is equal to the product of 1 minus f of p over p to the s over p. That's the formula that I wrote in first lecture. I used C, a little c for this f. I said if it is a multiplicative, fully multiplicative function, then have this identity. But now you're there on proof. So in this case, you can actually write f of p to the n is equal to p to the n, because it's fully multiplicative. F of p to the n, f of p n. Hence, sum is, so let's write it, 1 plus f of p minus s plus f of p2 e to the minus 2s so on. You can just write it as 1 plus f of p to the minus s plus f of p squared to the minus 2s so on. And by geometric series, this is equal to 1 minus f of p minus s in the geometric series. Okay. So the point is that this we didn't have the only multiplicative. The fully multiplicative case, again, right, is the conclusion. Okay, I mean, special case, of course. This is the original Euler product formula for zeta, right? That's what the Euler product formula. Zeta of s, which is the sum 1 over n s again. In this case, f is 1. Of course, it's fully multiplicative. So then we have this formula that sum 1 over n s is equal to product of 1 minus s minus 1. I mean, this is a special case of the corollary, which is just happens. Euler's zeta. Riemann's zeta function. Yes. Sorry. See. Sorry. Oh, from here to here. There. From here to here. Yeah. Yeah. So, what is geometric series telling you? Geometric series is this, right? 1 plus x plus x2 equal to 1 over 1 minus x, right? So now let x be f of p, p to the minus s. X be equal to f of p to the minus s. Then you are in business. Yeah, sorry, I just sometimes I jump, but I assume that it's okay to jump. But
you mentioned geometric series.
yeah. Well, yeah, I mean, sometimes I also jump without knowing that I'm jumping. I mean, so I'm assuming it's okay. I hope that is okay. I'm not going to fall, but sometimes you do fall. Okay. Cool. So, okay, so then now we want to do something really cool about zeta function. Do something, some really nice statement. So it relates to the question I asked about the convergence of the zeta on the critical line, not critical line, on the line s equal to 1. Didn't know what's going on that line. There are no questions about this, I can place it. All right, so let's erase this then. So how we place this again? Yeah. So proposition 1. The first one is we have already done. I mean, there's nothing but I just write it. Zeta function is holomorphic in real part of S bigger than 1, which you already know. Second one is that, oh, we didn't know, that zeta S has a meromorphic extension to real part of S bigger than 0, real part of S bigger than 0, with a simple pole, is equal to 1. Moreover, zeta of S equal to 1 over S minus 1 plus, I guess the notation is I use phi of S maybe, with phi holomorphic. This one is not meromorphic, holomorphic in real part of S 0. Okay, yeah, that's what. Okay, so one we have already proved that this guy is holomorphic in real part of S bigger than 1. Why? So 1A, but 2. So the situation is like this. There is this line S equal to 1. And we know that this is actually the domain of absolute convergence and the domain of convergence of this Riemann zeta function. Both match for this one. That's the line S equal to 1. You're okay here, you're holomorphic here. So, but what we want to show is that at least you can analytically continue zeta past this line at this new area in a simple pole at S equal to 1. And we also know the residue at S equal to 1. The residue is 1. So, because this phi is holomorphic, there's no problem at S equal to 1. And that's so much we can prove. So, if you prove that, in particular, it shows that zeta has a limit. It's nice. As you're approaching these lines, zeta has a limit because it becomes part of a new family of holomorphic function, a new kind of holomorphic function that takes over from here, but zeta should have a limit as you have. Now, in terms of being convergent on that line or not, I'm not not sure. That's the thing. Yeah.
But version 9, version.
Oh yeah, everywhere on the
Conversion somewhere and
hmm?
gotta be real. With what the
No. Remember, the argument was that we had this wedge, and the angle, the opening was everything less than pi was okay. The total angle less than pi was okay, but we never said at angle pi. So I'm not sure what happens exactly in terms of conversion, but certainly the function zeta has a limit as you approach this line, everywhere in this line, except s equals 1. Actually, that's kind of a good question to investigate. It's not very difficult, but it's good to know, and searching online a little. But that's not what we are claiming here. I'm saying something else. We want to prove something else. So now 2. For proof of 2. So for the proof of 2, we have to introduce another function. It obviously has analytic conjugation. Is already not analytic conjugation, it's holomorphic for real part of S bigger than 0, and we use it in a kind of nice way to get resolved into. So this function, let now eta of S equal to minus 1 over 1 to the S plus 1 over 2 to the S minus 1 over 3 to the S plus 1 over 4. So the function was actually introduced by Euler himself. Okay, so this eta is alternating sums of elements of the zeta function, but minus 1. Okay, what can we know? Okay, this is a Dirichlet series, right? What can we say about the domain of convergence of this Dirichlet series? What can we say about domain of convergence of the series? Real part of S bigger than 0, right? And actually, we studied this, we looked at this. So this is eta is holomorphic in real part of S positive by our general result. And it's not holomorphic for real part of S bigger than any negative number. Know that. So that's really the line that defines convergence. Yeah. All right. So now let us add eta to zeta. So zeta of S plus eta of S. What do we get? If you add, so this is zeta of S, 1 over 1 to the S plus 1 over 2 to the S plus 1 over 3 to the S. 1. See, the odd powers, odd terms cancel, right? And then we are left with 2 times the even thing, right? So 2 times 1 over 2 to the S plus 1 over 4 to the S, so on. But I can write this, I can factor 1 over 2 to the S. So this becomes 2 over 2 to the S times 1 plus 1 over 2 to the S plus 1 over 3 to the S, and so on. This is zeta again. That's the thing. Equal to 2 over 2 to the S times zeta of S. Now, there this story happens. This story is correct for real part of S bigger than 1, because zeta have no right for us to exist for real part of S. And so this is correct for real part of S. So then I can isolate zeta in this equation and write it in terms of eta. Let's write zeta in terms of. So we get zeta of S times 1 minus. So this goes to the left, 1 minus 1 over 2 to the s minus 1. S minus 1 is equal to eta of s. So you now you get that zeta of s is equal to eta of s. Okay, so this factor. So if you multiply, this is 2 to the s minus 1. This is 2 s minus 1 minus 1. And this is eta of s, right? So far, are we okay with this? Yeah. It's quite elementary. This is s minus 1. Yeah. Okay. That's what it is, yeah. Okay, so now let's focus on this. You get it? Is it upside down? Did I get it? Sorry? Zeta of s, I multiply by 2 to the s minus 1, and then I divide by this, I get that is sorry?
One.
Sign. Oh,
What is
Where it's 1 minus 2.
the denominator?
To be the other way around, like up 1.
Right here?
The top line.
Okay, oh, here, there's
It
a
should be the
problem.
other way.
Oh, wait a minute, so,
1 over 2.
oh,
It's 1 over 2 s minus 1 minus 1.
just a second, so it comes from here, because I just say 1 minus 2 over 2 to the s. Over 2 to the s is 1 over 2 to the s minus 1.
The over minus.
Oh, there's a minus sign. So the issue is only a minus
Yeah, the
sign.
issue is not by
Oh,
much.
just a minus sign. Okay, I agree with that. Yeah. Good. Good.
And
That's good. Yeah, good. 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 Okay, now let's look at this equation. This is the golden equation that is going to be showing the analytic function. So why? Look at this equation. Originally, we said that okay, both sides are defined on real part of s bigger than 1. But obviously, eta, we know that is a holomorphic function in real part of s bigger than 0. Here, this is okay. What about this function? What could go wrong with this function? Look at this function. There's nothing wrong with s minus 1. That's holomorphic everywhere. That's like exponential function. It's basically exponential of s minus 1 times log 2. So that's exponential. Now, the denominator, however, at s equal to 1 has a pole. So if s is equal to 1, get 2 to the yeah, 2 to the 0 is 1, so you get minus 1 plus 1, you get 0. So let me write it down because I wanna also have more space. So now the claim is that that part is minus 1 over 1 minus 2 to this minus 1 is meromorphic on C in unique simple pole that's equal to 1. So certainly it has a pole at s equal to 1 because the denominator is 0, becomes 0 at s equal But the thing is, we have to understand the nature of the pole. I'm saying it's a pole of order 1, so it's a simple pole, and I want to also write the structure of the pole in terms of. Okay. Now this is a simple comprehensive PhD complex analysis comprehensive question. So you know how to do it? You know how to do this? Yeah. How do you do that? Yeah. How do you write the Taylor expansion or Laurent expansion? Yeah, but there is an elementary solution, actually. This is just a purely elementary solution to this. And exactly. Yeah, when nothing works, just think about geometric series. That's going to be your savior. It's really amazing, how powerful geometric series is. So use geometric series, indeed, yes. So what we can do in this case, okay, so geometric series 1 over 1 minus x equal to sum 1 plus x plus 2, so on. So how I'm going to use geometric series in this case, by the way. This is correct, but how am I going to use it for that?
Here's how.
2.
Right.
Uh-huh.
1 over 1 minus.
Yeah.
That's the series.
So let's see. But although I saw something not very forthcoming in this argument, but so because I have 2 to the s minus 1 now. Okay, so s minus 1, when s is near 1, yeah, this is smaller than 1, so it's okay. I can do the expansion. Okay, so I just write it as 1 plus 2 to the s minus 1. But you see, it still doesn't help me. I want something else. No. No, I want to see some 1 over s minus 1 factor plus phi of s here. That's the okay. So yeah. Also, yeah, we can. I mean, if worst comes to worst, we can always use L'Hopital. And
Yeah, yeah. Exactly.
But I mean,
There should be a way to expand it, yeah.
yeah, this morning I did it halfway through, and I was convinced that this is trivial. So, so I left it, and I'm pretty sure it's we can do it. But okay, so do I have any notes on that? No, I don't think so. No, this was all. So maybe there is already. Yeah. No, I just say zeta s has analytic continuation to real part of this. Just write the statement as is. I mean, no proof I have. I have no proof here. Yeah. Oh, I just say, yeah. So the claim I'm making is that, yeah, the claim I have is that 1 over 1 over 1 over s minus 1. Why is it like that? S minus 1 and 1 minus s. Uh, no, that's okay. That's 1 over 2 s minus 1 equal to 1 over s minus 1 plus k of s k holomorphic real part of s. I mean, it's just k holomorphic everything. See. We are saying that we can actually isolate this thing completely. The pole can be completely isolated like that. Okay. Okay, so let's do this in the break. Better to do it not in front of the camera. Maybe we just do it in the break, and then okay, yeah, that's the best. Okay, so and eta is okay. Eta is holomorphic for real part of s bigger than 1. Though I mean, still I have this challenge of I have to see what is of 1. But how to see 8 of so what was 8 of s? 8 of s was minus 1 over 1 s plus 1 over ds minus 1 over e to the s so on. So this is equal to negative. So this shows that 8 of 1 is equal to, in case we are interested in value of 8 at 1, is equal to minus 1 plus half minus 1/3, so on. Do I have to know the value of this by any chance? Okay, so imagine you want to know the value. Do you know the value of this guy? Feeling Leibniz calculate. You think there's a pi? So let me write expansion of log 1 plus x. Oh, sorry, I noticed I was watching the videos actually myself. I noticed I have said ln in some places and log in some places. They mean the same thing and they mean really log. But in higher mathematics, you never say ln, you always say log, and you mean in base e. The base 10 is legit, actually. It's not natural. I mean, except for humans, have 10 fingers. I mean, that's just e is the natural. So the mathematicians always call log base e. But that's okay. So I didn't want to create any confusion for that. So just for curiosity, let's see if we can compute it on the spot here. So what is the expansion of log of 1 plus x? With signs,
yeah.
with signs or without signs?
With signs, because you get 1 minus x.
Yeah. So I'm planning this is x minus x2 over 2 plus 3 over 3 minus x4 over 4. That's what it is. So how do you prove that? Oh, is that the assignment?
Yeah.
Okay,
so
the negative was minus x.
Yeah, but then it's the same proof.
But how do you prove it, by the way? Maybe you don't want to show it because it's assignment. Okay,
I will say
that's why. Okay, so let me just check that I'm not off by a negative sign because I don't want to. So I just privately check it for myself. I won't tell you. I have a way of testing this. This seems to be okay. Okay, then put equal to 1. Get ln 2 is equal to 1 minus half plus 1/3 minus 1/4. And here we have this. So this is equal to negative 8 over. So 8 over 1 is negative 1. This is what we wanted to compute. Okay, so do I need this? I'm not sure. Because now I'm a bit completely think about this. So in the break, maybe we have to use this as well, maybe we don't. But so for now, I just put a halfway home, not home yet. We'll get home over the break. But this is a very important result because it really tells us that now the Riemann zeta function all of a sudden now can be extended all the way up to here. We are part of S bigger than 0. Of course, S equal to 1 is a simple pole with residue 1. That's so this is really a good thing. Now, pushing this to the left takes much more energy, creativity than this method. This is very elementary method. To show that actually Riemann is a function as analytic whole complex, have to have some new ideas. That this elementary manipulations doesn't work anymore. So this was like Eulerian, but Mannian. So Riemann actually proved that this can be extended to the whole. And so there is a holomorphic function that coincides with Riemann zeta this region, holomorphic except that's what we call Riemann. And he gave 2 proofs of that. I will give you 1 proof, maybe. Okay. Any questions? Yeah, you have to think about this issue of analytic continuations because that's kind of it's a very mysterious process. I mean, it's not. Yeah, just think about it. It's quite. Yeah, it's yeah. Okay, so what else I wanted to do? Right. 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 So now I want to do something which did in a different form in even in the first lecture, but now it's more precise form. So this plane. What I want to show now is so plane is that when S goes to 1. Now let's let's say from real numbers on the positive side, we have sum of 1 over S over P asymptotic log of 1 over S minus 1 as S goes to 1 plus. This working just with real numbers makes sense to take log of positive real number 1 over S minus 1. S is bigger than 1. And this is system. Remember, we just say for functions f of s, it has including of s as s goes to 1 plus. This means that lemma goes of s over g of s goes to 1 plus 1. So we are assuming that both functions are defined on the real part of s bigger than 1 on the real axis, for example, at least. or nearest one, and that's the meaning of this statement. How we can prove this? Okay, so this is like related to the statements that we had, that sum of 1 over p equal to infinite, and also Euler's statement that sum of 1 over p equal to log infinite, things like that. So it's kind of related to that, but that's way different. So we'll take log of both sides of Euler product formula. So in other words, you have this sum of 1 over n s, or it's zeta, for example. Is equal to product of 1 over minus 1 over s. And this one? Yeah. Okay, so if I take log of both sides, then you get log of zeta of s is equal to log of these things on the right hand side, but there's a negative sign that comes in front, so this is minus, and log of product is sum of logs. On sum log of 1 minus 1 with 2. Now, this on the right hand side, I can use that formula for log of 1 minus x that I wrote. So I've got log of 1 minus 1 over p to the s. What is that? That's sum of 1 over k e to the s, right? K from 1 to, oh, ks here, sorry. 1 over, so what was it? See, I'm using this formula now. Log of 1 minus x equal to sum of xn over n. And I'm just letting x to be equal to 1 over p to the s. Now here I should say k maybe. Like that. Right? Okay, so then you just add all those terms. So then so now right hand side of the star equal to sum over k, sum over primes. Yeah, that's what it is. So there's a minus sign here, and then I've got 1 over k e to the s. Now, I can write it as minus. So I isolate, well, I mean, this k goes from 1 to infinity. I isolate the term k equal to 1. Okay. Term k equal to 1, I just get minus sum 1 over then t to the s over all primes. That's the part I want. And then I just say plus sum k bigger than equal to, and sum over p 1 over k p is. This is the right hand side after I take the log. Now, I claim that this whole thing actually is finite. and find it for all s. It's real. Why is that so? What can you say about something like this? K bigger than equal to 2. Well, that was by the p test. Well, p is not a prime. I mean, p is k. K is bigger than equal to 2. Well, I mean, these things are convergent. But not only that, but also if you take different values of p, the total sum is also less than infinity. So this double sum is really less than. That's one of your assignment questions. We will diligently work on that, and so it doesn't take more than 5 minutes. So this whole thing then is finite. So I've got this part then plus something which is I can write now minus sum over p 1 over s plus k of s. And k of s is good at s equal to 1. K of s, I mean, actually k of 1 really is less than, not just singular one, k of 1 also, because 1 you get squares and so on, powers. There's also a damping factor even 1 over k in front, so even if it's smaller, that doesn't matter. Right. So now what we have got this sum of 1 over p s, this one, in this k to the left hand side, and then with log of z, log of zeta of s. Zeta of s, we know the behavior of zeta of s near s equal to 1. Okay, so write it then. So draw that. At least partially we saw, it didn't completely prove, but we saw partially that zeta of s can be written as what? 1 over s minus 1 plus phi of s, right? That was the thing that we had. So now we have got here log of 1 over s minus 1 plus phi of s is equal to minus sigma 1 over p to the s plus minus k of s. This is holomorphic, the real part of s bigger than 0, and this is also holomorphic, s equal to 1 at least. And what we wanted to show, we wanted to show that some 1 over p to s or is asymptotic log of what? 1 over s minus 1. And this goes to 1 plus. So I claim that double star implies the last thing. There's a minus sign here. Have mistake somewhere for this sign. I would rather to have this log of 1 minus s because this phi is holomorphic, so really it does not contribute. This is okay. Right. So let's also think about it in the break. So also, but let's think about the thing, the two statements that. So, any questions or comments?
That's just a home.
Sorry.
I is just home.
Phi is holomorphic, yeah. Holomorphic, where? It's better than that.
That's right.
Huh?
Positive.
Well, I mean, if it is holomorphic, it has to be defined on an open subset of complex numbers. Just say real, then it's not doesn't have, it's not an open subset of. Yeah, real part of SK. So that was the domain of that's right. Definitely phi. Yeah, it's holomorphic there. Was that the question or? Yeah. So phi is holomorphic here, but we have to use something more here to put that's the state from this. And we haven't put. Yeah, this is part of the first thing that. Yeah, exactly. We haven't completely. Right. Other questions or comments? So we can take a break now. So.
Chairs are really gone. Yeah.